Okay, so this PowerPoint is going to be a review, a little bit of Coulombs Law. We're going to work a couple of problems together, and then that should be enough for you to be able to work the problems that are going to be done in class on Monday. So let's just review kind of quickly what Coulombs Law is. It deals with charged particles and how to determine the force that exists between two charged particles. It is an inverse square relationship between the force and the distance between the particles. So if you have two particles with charges Q1 and Q2, and depending on what distance they are apart from each other, the farther they get away, the force decreases as an inverse squared. And I should say, I don't know what we used last year, if we used R or D, but this year we're going to use R for our distance between the two charges. So I just wanted to remind you, the formula for Coulombs Law, we usually drop the C and we just say force, but I just wanted to, it's FC for Coulomb, equals K. K is Coulomb's constants, 9 times 10 to the 9th newtons meters squared per Coulomb squared. Q1 and Q2 are your two charges. Remember that those are in coulombs. That's what our unit for charge is. And R is the distance between the charges, and that's going to have to be in meters. So that was the formula. If you remember when you worked this problem, if you work them out and you end up with a positive answer, that means that the two charges have the same sign, and that's going to be repulsive. And if you work it out and you end up with a negative answer, that means one charge is positive, the other's negative, and that's an attractive force. So you want to keep that in mind. That does not speak to what direction the actual force is, because you have to look at the scenario and see what direction the actual force is going to be. It only speaks to whether or not the charges are trying to push each other apart or pull each other together. So that's really all that's going to speak about. I wanted to remind you also that force was a vector, and so therefore it has a size and a direction, and when we draw it, we're going to draw it like a vector, like an arrow, in whatever direction we need to draw it in. And when we add and subtract forces, we're going to add them like we add vectors, which remember means that they're not just numbers. You have to take the direction into account. So if I have two forces acting on an object and they're both pointing in the same direction, like this one is 5 newtons and this one is 3 newtons, then the net force, the total overall force, in this case would be a total of 8 newtons because they're acting in the same direction. Likewise, similarly, if I had 5 newtons pulling one way and 3 newtons pulling back the other way, my net force would be, 2 newtons pointing to the right. And I should say up here that this net force really is 8 newtons pointing to the right. Similarly, if I have two forces where one is being pulled this, one force 5 newtons up this way and another force 3 newtons that way, you don't make the net force like this. I want to remind you, don't do this. This is bad. Boo, hiss. Don't do that. If you have two forces, one up and one to the right, you need to do the tip to tail method. 3 newtons, 5 newtons, and this would be the net force right here. So this was all stuff that we did over the summer and some last year too. Figuring out that net force, you'd use Pythagorean theorem, and if you needed to know the angle, you would use trig functions to find the angle. Okay? So let's do a problem with some multiple charges. Coulomb's law with multiple charges. We have 3 charges in a row that we want to calculate the net force on this third particle out here due to the other 2 particles. So I'm going to just look at it and say, all right, this third particle is being repelled by this first one. The first and the third, they have the same sign, they don't like each other. So that means that it's trying to be pushed away from the first one. So I'm going to draw that force on here, and I'm going to label that force the force of 1 on 3. So that's how I'm going to label it, the force of 1 on 3. And that means 1 is trying to push charge 3 away from it. Meanwhile, charge 2 is trying to attract charge 3. So there's another force on charge 3 due to charge 2, and it points this way, trying to pull charge 3 over to charge 2. And I'm going to call that one the force of 2 on 3. And these two forces are opposing each other. So if I want to figure out the net force, I'm going to have to find these two and then subtract them because they're in opposite directions of each other. So that's what we're going to do. We'll figure out the force of 1 on 3 and the force of 2 on 3, and then we will subtract the two numbers. Now, I'm going to just figure out the magnitudes of the forces. I'm not going to worry about the positives and negatives, because the positives and negatives are purely meaning attractive and repulsive. They are not corresponding to the directions of right and left. So I'm going to just figure out absolute value of these forces. So this is going to be K Q1 Q3 over R squared, which is going to be 9 times 10 to the 9th, negative 8 times 10 to the minus 6, that's what that microcoulomb means, negative 4 times 10 to the minus 6, divided by the distance between those two is 0.5 meters, and I'm going to square that. We don't want to forget to square that number, you'll owe me money. That gives me 2.7 newtons, and that is going to be pointing to the right. Nope, I apologize. That's the wrong number. Let me erase that. It is going to be pointing to the right. That part is correct. But it is not going to be 2.73. It's going to be 1.152 newtons to the right. I'm going to do the same thing for 2 to 3. It's going to be K Q2 Q3 over R squared. So that's going to be 9 times 10 to the 9th, 3 times 10 to the minus 6, negative 4 times 10 to the minus 6, divided by 0.2 squared. And that's the one that gives you 2.7 newtons pointing to the left. So now if I want to figure out the net force, I subtract these two numbers because they're pointing in opposite directions, and my net force ends up being the subtraction of the two is 1.548 newtons to the left. So that's how that ends up working out. So I just want to remind you, because those are sometimes problems that you have to work. Another type that you're going to see is these problems where you have to figure out where you're going to put a charge so that's in equilibrium. So for example, we have two charges. They are 3.6 microcoulombs. I'll call this one Q1. And 4.4 microcoulombs. I'll call that Q2. They're both positive. So they want to know where in between those two, and they happen to be 0.3 meters apart from each other. So that's the distance. Now the question is, where am I going to put a third charge? Let's suppose this is my Q3. The third charge's value is 2.4 microcoulombs. Where am I going to place it so that it does not feel any net force? So another way of saying that is it's in equilibrium. That's the word we use. So what we're going to do for this one is we're going to say that this distance is going to be x, and I'm going to find x. That makes this distance 0.3 minus x. You might remember doing these. We did these last year. So I don't know how well we're going to remember that. The key to this being in equilibrium is that the force of 1 on 3 and the force of 2 on 3 have to be equal to each other by magnitude only. Okay, so 1 and 3 and 2 on 3 both have to be equal. That makes Q3 will be in equilibrium when that happens. So the force of 1 on 3 and the force of 2 on 3 will balance each other out. Okay, so that means K Q1 Q3 over the distance between 1 and 3 is x, so that's x squared, equals K Q2 Q3 over 0.3 minus x squared. So that's what I've set up here. So K, Q1, Q3, those are the two charges interacting between those two, Q1 and 3, and then 2 and 3. Now I can do a little canceling, so that we simplify this a little bit. The K's go away. There's one on each side. There's also a Q3 on each side. So we'll get rid of those. So I'm going to end up with Q1 over x squared equals Q2 over 0.3 minus x squared. So I'm going to plug in Q1 is 3.6 times 10 to the minus 6 over x squared, and Q2 is 4.4 times 10 to the minus 6 over 0.3 minus x squared. I'm going to do one more little bit of canceling. I can get rid of those 10 to the minus 6's. There's one on each side. And then I'm going to cross these up. So I'll have 4.4 x squared equals 3.6 times 0.3 minus x squared. The easiest way to do this is not to FOIL that out, but rather to take the square root of both sides. And when you do that, you would end up with, on this, well, depending on how you set it up, you'll end up with 2.1. Let me see if I have this set up right. Hold on a second, I'm going to scroll up. Let's see. 1 and 3 and 2 and 3. X and 0.3 minus x. Okay. I think I'm okay. So this is 2.1 x squared, x. And this is 1.89 times 0.3 minus x. And then you just solve that out. And I'll let you finish solving that. At that point, it's just algebra. You just need to solve that out. Okay? So that is the, that's how we work that. That's the other problem. So now you are ready to go and finish the review sheet if you haven't finished it already, and be ready to do some problem solving in class Monday.